2-point boundary value problems for ordinary differential equations. And we briefly discussed a possible physical problem that leads to this kind of mathematical problems. Just to refresh on that, let me briefly introduce another example. It is not the same example we considered last time. Let's consider a metal rod, which may actually be a nail, for example. Metal rod. One end of this metal rod is placed, for example, in ice, and another end is placed, for example, in some hot environment with accurately controlled temperature. So we can say that on this end we have a temperature of, say, 1000 degrees C, and on this end we have a temperature of 0 degrees C. And we want to know the temperature distribution along the nail, along the length of the nail, or the length of the rod. We introduce a coordinate system. I didn't make it horizontal, I'm sorry. It's my poor drawing capabilities, but it should be. So it's a one-dimensional problem at this point. So we say that we are considering our rod at coordinates from A to B, and we fix the temperature. We want to find the temperature distribution along the rod. So what we need to know about the rod, we need to know its conductivity coefficient, which is measured in watts per meter per Kelvin. What else do we need to know? It is possible that the rod is heated up or cooled down along its length. So we can imagine that there may be some heating coils around this object, or some cooling devices that may cool down some other parts of this object. And to make the problem more general, we introduce a function f of x, which is a specific power of heat sources or sinks along the length of the rod. So for every value of the coordinate, this function may take some specific value, either positive or negative, depending on whether we want to heat up or cool down the object. So, in these assumptions, let's write the differential equation that describes the temperature distribution along the rod. If this parameter is constant, then we would be able to write the second derivative. Let's denote the temperature, for generality, let's denote the temperature with the letter U rather than T. So we can say that we have a second derivative of the temperature. And on the right-hand side, we have f of x. And here we should also have a thermal conductivity. What else? We can also imagine that this heat sink or heat source also depends on the temperature itself. So the example of such behavior is some chemical process. If we have some chemical process occurring in the body of this rod, and in this process we have heat supply or heat sink, then this function may also depend on the temperature itself. Let's assume that this dependence is linear for simplicity. So in such conditions, we will need to add another term in the equation if we have a linear dependence of the heat source on temperature. And I'm writing this term on the left-hand side just because it contains an unknown function u. So, as I said, on the ends we have a fixed temperature. Well, let's keep it. No. It's better to change the letter. Let's call it UA, and in our particular case it is T0. And on the other end we have UB, which is in our particular example is T1. I should better say that these are functions with tilde to let me divide all the equation by lambda and say that we finally have I just divided the whole equation by lambda, so r of x is equal to r tilde of x divided by lambda, and f of x is equal to f tilde of x divided by lambda. So today we are considering this type of problem. After some theoretical discussion regarding the existence and uniqueness of solution, last time we have discussed one method to approach this kind of problems. In that method, which is called shooting method, we replace the boundary value problem. This problem is called the boundary value problem because the values of our unknown function are defined on both ends of our computational domain, unlike for the Cauchy's problems when both conditions would be defined on the left or the right end. Right? In the Cauchy's problem, we define all conditions in one point, usually. And for the second order equation, for the Cauchy's problem, we would need to define the function value and the value of its derivative at the same point. Here, the situation has changed. We have two values at two other different ends, and the conditions for the existence and uniqueness of the solution are much more restrictive for this case. We discussed it last time. Please look at the video. Look through the video. One important condition that I want to mention today, discussed last time, was that this coefficient r of x must be positive. So our goal is to solve this kind of equation. So I will remove tildes from here and remove this intermediate writing from the right. Okay, and I will remove lambda from here. So we need to solve this kind of problem. How can we approach that? One approach was shooting, and another approach is the finite difference method. What means the finite difference? We replace the continuous derivative here in the equation with its counterpart, with its approximation through the values of the function u at several points. And when we discussed numerical differentiation, we discussed how to do that, right? So if we introduce a mesh on A, B, x1, x2, and so on, xi plus 1, and so on. So we have a mesh, and we have some function u of x that we don't know. But we can say that we will be looking for the values of this function only at the points of our mesh, as we did before, and we need to approximate this derivative. How did we do that? For example, we can use a well-known second-order approximation formula. And to make this an exact equality, I have to add an O capital, some remainder, which is of the order, depending on h. No, it is of the order 2. You can prove that by expanding this and this guy into Taylor series.
Yes.
We did that. So, making an error of this order, we can write, instead of the original equation, we can write this finite difference equation. So, how do we approximate this term? The question arises, how do we approximate this term? The easiest or the simplest approach is to take it at the same point where we approximate the derivative. We can do something else if we have reasons for that. If we know something specific about the behavior of our solution, we can use another approach. We can use the average of several points and so on. But it would not change the whole order of approximation for the whole equation. And we take this right-hand side also at point I. So what do we get? Let's rewrite it in a little bit modified form. So we explicitly take out ui plus 1, write ui minus 1 on the first place, and ui plus 1 on the last place. So before the ui minus 1, we have a coefficient 1 divided by h squared, right? Plus what? Plus r of xi. Oh yes, that's right. Minus, not minus, but plus 2 divided by h squared. And the last thing here is the coefficient before ui plus 1, so it is the same as the coefficient before ui minus 1, h squared. And on the right hand side we still have this fi. Let me, for the simplicity of notation, I replace f of xi with fi. And here I do the same with r. Ri. So this equation is valid. Where is it valid? For which points of our mesh this equation is correct? This equation is correct for all internal nodes of our mesh, right? But not here and not here. Because the ends are defined by the boundary conditions. And these boundary conditions may be different, may be more complex. We'll consider this case a little later. So here I goes from 1 to n minus 1. So we have how many unknowns? We have n plus 1 unknown, and we still have only n minus 1 equation. So we need to add two equations, which are u0 is equal to ua and un is equal to ub. And this is how we obtain a closed system of linear algebraic equations that we need to solve. So what do you know, or do you see what type of the system we get? Fine. What is specific about this particular system of linear algebraic equations? How many different unknowns are involved in each equation at maximum? Only three. Only three unknowns of all the unknown values of our function along the mesh are involved in each particular equation. And in the first and the last equation, only one unknown is involved, and the value is defined by the boundary conditions right away. The system of linear algebraic equations of this type is called tridiagonal system. Did you hear about this somewhere before? Okay, then I need to explain how to solve this kind of systems more efficiently than the general type of system. Solution of tridiagonal systems of linear algebraic equations. Thomas algorithm. I'm saying Thomas algorithm because I'm speaking English. If I was speaking Russian, I would say метод трехдиагональной прогонки. That's fine that you don't know. I'm giving you some references that you will meet in the books. If you read some books at some point, you need to read some books. You need to recognize various methods. So, Thomas algorithm or метод трехдиагональной прогонки. И еще часто говорят, что этот метод Гельфанда-Лукуциевского, который был разработан в 1950-х годах у нас и примерно в то же время за рубежом. 1950s. So, the general view of the tridiagonal system looks like this. The ith equation involves three coefficients. Plus b I u I plus c I u I plus 1 is equal to d I, equal to di. This is the ith equation. Let's write the first equation in the most general case. b0 u0 plus c0 u1 is equal to d0, and the last equation would look like un minus 1, and before that cn is present, then bn is present here, and cn is present here, is equal to di m. This is the general form of the tri-diagonal linear equation system. So, unlike in our case, when in the zeroth and in nth equation we only have one term, I'm introducing two terms here to keep the tri-diagonal structure of the matrix everywhere. So everything here and here is 0, and the elements on the diagonals may not be 0. They can be 0 still, but in general they are allowed to be non-zero. How to solve the system of this kind? What is this Thomas algorithm or Gelfand-Lukutsievsky algorithm? The idea is the following. Let us express the next unknown, like u. No, let us express the ith unknown through the next unknown. That is the first step. We will use some coefficient alpha and beta here. Let's express the next, the ith unknown as a linear function of the next unknown, and see what we get if we do so. I'm not sure. Probably the coefficients here will be I. So let's start from the beginning. u0, let's express it as a function of u1. So u0 is d0 minus c0 u1 divided by b0. d0 by b0, c0 by b0. And I swapped the terms now, so I need to say that this guy is called alpha 0, right, together with the minus sign, and this guy is called beta 0. So I obtained the desired form. What's next? Let's express the next u1 through the u2 unknown. How to make that? How to do that? So we imagine that we have 1 here in this equation, and we write du1, and we know that we'll need to divide by b1, right? b1. What's next? So we have minus. This guy becomes c1 by u2 divided by b1. Okay, and also a1 by u0. a1 multiplied by u0, right? Do you see it? But instead of u0, I will put its formulation through u1. Here. Let me see. So alpha 0 u1 plus beta 0, and I can express u1 from this relation. Can you say what would I get if I express u1?
It's the better one. You can combine just, yes.
So I want the coefficient before u2, and this coefficient will remain the same as in the previous equation, actually, right? So the coefficient before U2 is just minus C1 by B1. I think I have lost something, but we'll find everything I lost. No, I need more space. I'm sorry. I will start from the new location on the board. I don't need these equations any longer. So we formulated them. So again, U1 is something before U2. Here we had C1 by B1, but we will also have to divide by the coefficient that goes here before U1 after collection of all the terms before U1. Okay? So, and what else? We have this free term plus D1 by B1. What else do we have? Minus A1 by beta 0. Right? A1 by beta 0. And before U1,
A1 by B1 also should divide the confusion.
yeah, that's right. Let's keep this coefficient for the moment here to avoid mistakes. So 1 minus or plus 1 plus A1 by alpha 0, right? Like this. Okay, what is alpha 0? Alpha 0 is minus C0 by B0. Let's express now. What's that?
For beta 0, A1 divided to B.
I'm not sure I got your comment. Did I make a mistake?
Yes.
What's your comment?
Where beta 0, the coefficient before that, A1 divided by B1. No?
Yes, just a second. Let me check. So what did I do? I expressed
Because
U1. This is divided by B1. This guy is divided by B1, that's right. And this guy goes to the right and is divided by B1. By B1. Is that correct?
Yes.
Fine. Thank you. So, C1 by B1 and 1 divided by 1 plus A alpha 0. Right? U2. Let me see. D0 by B0. No, it doesn't work.
Это там тоже должен быть скобчик еще. А1 перед альфа.
Here. Okay. D1 minus A1 B0 divided by B1 and divided by what? I can say this and this, right? Okay, do you agree? And I can do the same thing here. And then B1 cancels out in the denominator and numerator. And finally, I get the formula that I want. C1 divided by B1 plus A1 alpha 0, U2 plus D1 minus A1 beta 0 divided by B1 plus A1 alpha 0, and that's it. So we denote this by alpha 1 and this by beta 1. Again, we expressed the first unknown through the second unknown. So the general formula can be obtained by replacing 1 in this formula with I, and 2 in this formula with I plus 1. So this is how we get this relation, alpha I plus beta I. Replace in previous formula 1 with I, 2 with I plus 1. Okay, but how it helps us solve the system? So this procedure that we have just described is called the forward path or forward loop of the method. Stage 1, forward loop. The goal of this forward loop is to form the set of these coefficients, two sets of coefficients, set of coefficients alpha I and set of coefficients beta I, from 0 to, let's see, to n, from 0 to n. And let's write down the formula for the last unknown. This formula can be obtained from this last equation. dn divided by cn minus bn divided by c n multiplied by un minus 1. And here we can substitute the expression for un minus 1 using this formula. And then we will express un again, as we did before. Do you follow? If we, I expressed un from this last equation of the system, right? And I see that un depends on the previous unknown. But we have developed a new formula during our forward path. We developed a formula for un through un, for un minus 1 through un.
Okay.
We can use now this formula. dn by cn minus bn by cn. And here I put alpha n minus 1 un plus b n minus 1. And after that I express un from this equation. All other terms in this equation are already known, right? We already know all other terms. These are just coefficients of the original system or something that is expressed through these coefficients. Let's do it. un is equal to dn by cn. So dn plus, minus beta n minus 1 divided by cn. So I just multiply this coefficient by this. And bn, I forgot bn here. Okay, this is the free term. And here I have 1 plus bn by alpha n minus 1 divided by cn, right? So, similar to how I did before, I can put it over the same denominator, cn plus cn. Did I do it right?
Yes.
Okay. And then finally un is equal to dn minus beta n minus 1 bn divided by cn plus bn alpha n minus 1. bn alpha n minus 1. And that's it. Why do I say that this is the solution? This defines the solution. Because we know un, and we can express all the other coefficients going back. This is the end of the forward loop, and then goes the backward loop. Which is just the application of this formula continuously. Apply this formula for I from n minus 1 to 0. The positive feature of this algorithm is that it is extremely fast as compared to the algorithm for the solution of general systems of linear algebraic equations. The algorithm that you probably know is Gaussian elimination, right? Алгоритм исключения по Гауссу. So it makes the matrix triangular. But the complexity of Gaussian elimination complexity is O of n to the power of 3, where n is the number of unknowns. So we have n plus 1 unknown, so n plus 1 to the power of 3. And the complexity of this algorithm is only O of n. Much more attractive, thanks to the special type of the matrix that we obtain here. And this is the typical situation when you apply the finite difference method for the approximation of the boundary value problems for the differential equations, if you use regular meshes. In one-dimensional case, it's probably not very clear what I mean by regular meshes, because all meshes are regular. I don't mean that the mesh should have the same step. You can have varying step, and still you will have the tridiagonal matrix, or you may have not the tridiagonal, but you may have more diagonals in this matrix if you involve a more complicated way of approximating the second derivative, or any other derivative that you have. You can have a 5-point scheme, 4-point scheme, whatever you like. Depending on the number of points that you used, you will have the number of diagonals in this matrix. But for every case like that, a little bit more sophisticated version of this tridiagonal elimination algorithm can be developed. 5 diagonal versions are known and described in the literature and so on. But in multidimensional case, you may have a mesh like this. Let's think about 2 dimensions, for example. You may have a mesh like this, which is regular, and every node of such mesh can be denoted by 2 indices. So this pair of indices is unique for every node of such mesh. This kind of meshes is called structured meshes. And for the structured meshes, you will get this diagonal structure of the matrix. But in modern problems, people consider complex computational domains very often. And for such complex computational domains, it becomes a very tricky separate problem to build the mesh of this kind. It is still possible if you divide the area into sub-blocks, which are topologically equivalent to the square, and then divide each block with a regular mesh. It's still possible, but it's a lot of work. That's why currently people more and more use irregular meshes like this, unstructured meshes, so to say, built of triangles or even polygons of general type with arbitrary number of nodes.
But in this case, E and G also unique for each.
In this case, you cannot define a pair of indexes in a natural way that would correspond to every node. It becomes much harder to say which node is next to this node, because it will depend on the configuration of different elements around a particular node.
But we can say which will be next.
Yes, if you build a graph structure, connectivity graph for the nodes, you still can say who is the neighbor, but this neighbor will not be necessarily placed in a priori known mesh direction. It may be in the direction to the bottom, in the direction to the top, or it may be diagonally placed.
But in the first case, there is only one direction on the node.
if you can build a mesh like that, even for this case, you introduce new coordinates, which can be translated into these square coordinates.
Yeah, and this square coordinates has only one direction, so we can't make, for example, zigzag line.
I'm not sure I understand the question.
Like E and G always should be greater than previous E and G.
Yes, in the meshes like this, you know that that the neighbor to the right in I direction has the number I plus 1. And this simplifies everything. This simplifies this approximation and so on. Finite difference method can be applied on irregular meshes as well, or the versions of the finite difference method are applied in case of such meshes, but you will not get this nice structure of the matrix. You will get non-zeros here and there, depending on the number of this node and its neighbor nodes. These numbers they are usually not naturally connected. You cannot say that the number of my neighbor is my number plus 1. It may be plus 1, plus 10, plus 100, or plus 1055. And depending on these numbers, you will have 0 here, 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 somewhere, like a cloud of non-zero values. The matrix will still be what people call sparse matrix. A sparse matrix, meaning that there are a lot of zeros in this matrix. Only a small number of elements can take non-zero values. And this simplifies things as well, but you will not be able to apply this algorithm to solve such system of linear algebraic equations. Okay, what's next? We need to discuss some conditions that ensure that this algorithm will work out to the end. You see that in the denominators here and here you have some expressions depending on the coefficients of the matrix. And it is possible that these expressions go to 0. Right? If this unlucky case happens, you will not be able to proceed with this tri-diagonal algorithm. You will not be able to get the final solution. At this point, the algorithm crashes if this denominator is 0. And there is a theorem that provides conditions ensuring that none of these denominators is 0. Let me formulate this theorem. So the conditions are pretty typical and pretty simple, and they are simple to check. If the absolute value of every coefficient bk standing on the diagonal is higher than the sum of absolute values of of the off-diagonal coefficients, and if the coefficient standing on the diagonal is strictly higher by absolute value than the coefficient A in the same row, then we can guarantee that the Thomas algorithm will end up
in the first line. Maybe should do like b equals 1.
What's wrong with the first line? In our particular, in this first line, A0 is assumed to be 0.
Не, вот там же получается 0 просто будет.
Where?
Because bk in the...
Oh, I'm sorry. Sure, I didn't just... This is a misprint. So I will not prove it. If you're interested, you can find this proof in any reasonable book in numerical methods. But we have to control or have to check before applying this algorithm that in every row this condition is satisfied. This theorem doesn't say that it's not possible to solve such a system where the diagonal coefficient does not satisfy this condition. It's possible. It only says that the Thomas algorithm will not be able to solve.